Hello, welcome to your lesson on number patterns and sequences. Okay, we're going to take some notes. Please take only the most important notes. Of course, you don't have to write everything you're going to see in this presentation. Let's begin with some key vocabulary. A sequence is a list of numbers that is written in a defined order, ascending or descending, following a specific rule. For example, here is a sequence of numbers. And you can tell a sequence will have a specific rule if there's a pattern that you can notice. And here the pattern is pretty easy to see. From 3 to 7 we go up by 4. Then we go up by 4 again, up by 4. So you're always adding 4. So there is a definite pattern there. Therefore there will be a specific rule. In this case, the rule for this sequence is this. U sub n equals 4n minus 1. We can call this specific rule a general rule. Notice we're using U sub n. In the world of sequences, that's commonly used as your dependent variable. Okay, just to give you an idea of some more things here. So this is term number 1, term number 2, term number 3, or this is called position 1, position 2, position 3. So at position 4, for example, we have the term 15, or at position number 1, we have the term 3. So let's take a look at those words in this context. We have our sequence. The n values are domain values. If you look at this equation, normally you would see a linear equation like this written as y equals 4x minus 1. But instead of x and y, we're using u sub n and n. But those mean the same thing, right? They're just different symbols. So our domain, or the inputs, this value here, which would normally be x, that's our inputs. And our range is the outputs, or the u sub n right here, where the y would normally be. So in our domain, we have the numbers 1, 2, 3, 4, 5. And we know that because to create this sequence, we put the number 1 in here. And for example, if you put 1 in here, you'll have u sub 1, and then 4 times 1 minus is 3. So if you put a 1 in here, you get the first term. And if you put a 2 in there, so the next input 2, you'll get the second term. And if you put a 3 in there, you'll get the third term, and so on. So these are your inputs. They're always in order. And then your outputs are what you actually get from the rule. The rule produces the sequence. So these are our outputs, or our range of values. These values here are called the position, right? The x values are the position, right? Position 1, position 2, position 3, position 4, position 5. These values here are called the terms. The actual numbers in the sequence are called the terms. Okay, pause if you need to. This is all very important to understand how all these pieces work together. Let's go to the next bit here. So we have two types of sequences. One is finite, one is infinite. So finite sequence has a fixed number of terms, and an infinite sequence has an infinite number of terms. For example, this sequence here, you can see it begins and it ends with -3 here. It begins and ends, therefore it is a finite sequence. This sequence, however, has a beginning but does not have an end. It has a ... here, which is called an ellipsis, and that ... implies that this sequence goes on forever. Therefore, it is infinite. Also, we were talking about the rule, or general rule, for a sequence, and let me read this about that. A formula or expression that mathematically describes the pattern of the sequence can be found for the general term. So there's a formula or rule, and we use u sub n to express that rule, just like we did here. Okay, a sequence, two main types of sequences. There are many different types, but two main types are called arithmetic, is one of them, and we'll look at the next one in a moment. So an arithmetic sequence is when you add the same value to each term to get the next term. For example, we have this sequence, and as we proceed through the sequence, we can see we're adding 5 each time to get the next value. So that's like the one we just saw a moment ago. That's called an arithmetic sequence. Another example is 1, 4, 7, 10. You can see to get this sequence, we're always adding 3 to get the next number. So that's arithmetic. It can also be negative, such as -5, let's say. So let's see, -5 is the value we're subtracting. So 20, down 5, down 5, down 5. That's also arithmetic. All right, the other main type of sequences that we see commonly are called geometric. And these occur when each term is multiplied by the same value to get the next term. For example, we have 5, 10, 20, 40. So to turn a 5 into a 10, we multiply by 2. And then multiply by 2 again to make it 20. Multiply by 2 to make 40. This is now called a geometric sequence when we're multiplying to get the next value. Here, these ones can also decrease, just like we saw this arithmetic one decreasing. Geometric can also decrease, like here. We multiply by half here, multiply by half, and it decreases that one. So those are geometric. All right, TOK question. Do the names that we give things impact how we understand them? So we've called this one arithmetic. We've called this one geometric. does that affect how you look at these? Like when you hear geometric, for example, do you think about shapes? Geometry is typically about shapes, right? The study of shapes. So there's something in here that has to do with shapes. Interesting. I wonder why. So does that name make you think about something? Okay, let's try some sequences here. Our goal here is to look at the sequence and then make that general rule for it. It's pretty easy with these to look at it and say, hey, this one's going up by 3 every time, but what about the general rule? So one technique, and I'll show you for A, and then you can try it for B. One technique to find the general rules, we looked at it in class as well, but let's take a look. In A, you can look at this sequence as being created like this. So to get that first value, we can say 3 times 1 makes 3, and then 3 times 2 makes 6, and then 3 times 3 makes 9. So that's another way of writing this sequence. So we can see our rule will always have a 3 in it. There's always that 3. And then we're multiplying by 1, 2, and 3. Well, 1, 2, and 3, those are like the position numbers, right? Position 1, position 2, position 3. So our rule can be u sub n equals 3, because there's that 3, times n, which is the position number, right, n. And then that will work for any number in the sequence. This is arithmetic, because we can see it's going up by the same value every time. Try the same technique for this one and see if you can create the rule like that. Okay, check your work for B. This sequence, in this case, that first value term can be created by doing 3 times 1, the next one by doing 3 times negative 4, the next value 48 by 3 times 16, and the last one here by 3 times negative 64. So again, we can see the 3 appearing every time, but the second number, well, it's a 1, and then it's a negative 4, and then it's a 16. So how do we get those numbers? This is a little trickier for sure, but if you look at those numbers like negative 4, 16, 64, they're all powers of 4. So notice when we write the rule, like this 3 times 1 can be the same as 3 times negative 4 to the 0, because anything to the 0 power is 1. So this actually means the same thing as 1. Let's look at the next bit, 3 times negative 4. Well, 3 times negative 4 to the first power. And then the next one, 3 times 16. Well, that's like 3 times negative 4 to the second power. So we're trying to create something where we have numbers that are common so that we can then write it as a general rule. That's, again, very tough to spot that, but this kind of sequence is common, so once you see it this way, see if you can try this again for another one. But basically then our rule must be 3 times negative 4 to the power n minus 1. And why n minus 1? Because term 1, which was this one, the power was 0. So if that's term 1, that's not a 1 that goes there, it's a 0, so it must be n minus 1 to get 0. And here, this is the second term, but this is not 2, it's a 1, so we have to do n minus 1. So take a look at that closely. That's geometric, by the way. You have to be able to say whether they're arithmetic or geometric as you do this as well. And let's try the next one. So try C. And now check your work for C here. Take a look how that was written out. Very similar to the last one. No negatives necessary this time because these numbers are all positive. But again, 2 times something each time, so we know 2 is part of the rule. We have a 1, a 5, a 25, 125. How do you get those numbers? They're all powers of 5. So 5 to the 0, that's very common. That 1, 5 to the 0. To get 5, 5 to the 1, 25 is 5 squared, 125 is 5 cubed, and so on. So here's our general rule. 2 times 5 to the power n minus 1. Again, n minus 1 because this is 1 lower than the term number, always. Okay, I hope you're getting the hang of it. D is a little tricky. Let's see if you can come up with it. Okay, take a look. Take a look at the details. This one's a great problem. We have all of these fractions can be written like this, 1 over 3. The next one can be written as 2 over 2 plus 3. The next one, 3 over 7, can be written as 3 over 4 plus 3. So notice they're just searching for a way to write it where you have some common numbers. So we have that 3 appearing now in every denominator. Okay, look how it goes further. 1 over this one here, 1/3 turns into 1 over 3 plus 2 times 0. This one, 2 over 2 plus 3, turns into 2 over 3 plus 2 times 1. Wait, is that right? 2 times 1, 2. Yeah, that's right, because it's the 3 plus that. And then, and so on and so on. So it's always 3 plus something. So a little bit tricky, but in the end it comes up like this. The top numbers, you can see they just follow the position number, 1, 2, 3, 4. So that's n. The bottom one, we always have that 3, and we're always adding 2 times something. So 3 plus 2 times what? Well, this number is 0. this number is 1. So those are always 1 less than the term number, so 2 times n minus 1. So that's definitely tricky. It's been simplified a couple more steps here. This is neither arithmetic nor geometric, but it is definitely a little more tricky. So some of these take a little work. There's no actual process for it, right? Like a little bit of this would have been guess and check to come up with this, but you can do it for sure. Next one, let's try this investigation. So there are 2 gym plans. Please read about Lewis's plan and then Elijah's plan here. And our goal is to do these 3 things. There's a few more things that asked for here, but let's start with these 3 questions. Write the sequence for 5 visits under each plan, then write a general rule for each sequence, and then figure out when Elijah's plan will become more expensive than Lewis's plan, because Elijah's begins cheaper because he doesn't pay the 100. Okay, let's check. The sequence for the first 5 visits under each plan. Well, under Lewis's plan, he pays 100 membership plus 5 for that first visit, so 105 for the first visit. And then second visit pays another 5, so now he's paid 110 in total. And then 115, 120, 125. That's the total amount paid after each visit. And then for Elijah's plan, paid 15 for the first visit and 15 for every use. So after 2 visits, he's paid 30. After 3 visits, 45, and so on. You can tell Elijah's plan is going up quicker because this one's going up by 5 each time. This one's going up by 15. So this will catch up to that, but right now it's cheaper. Write a general rule for each. Well, using the same approach, in the first one, we have 100 plus 5 times 1, and then 100 plus 5 times 2, and so on. So the rule for that can be 100 plus 5 times n, because this is like our term number here. And for the second one, this is like 15 times 1, this is like 15 times 2, so we can tell our rule is going to be 15 times the term number, which is n. Now use both rules to find out when Elijah's plan will be more expensive. Well, to do that, you can take one equation and set it equal to the other. Imagine these are graphed on a graph. Where these 2 graphs intersect is where one plan becomes more expensive than the other. So I'm setting them equal to each other, solving like this by subtracting 5n, dividing by 10, n equals 10. So on the 10th session, they will have the same price, and after that, Elijah's plan will become more expensive. All right, some more vocabulary. A recursive sequence looks like this. It's a sequence where the previous term or terms are used to find the next term. So the general term will include the notation un sub n minus 1, which means previous term. Let's take a look. We have this here, and it says there's our general rule, but this is recursive because we can see instead of n in this equation like we had prior, we have u sub n minus 1. So when you see that in there, you know it's a recursive rule. And to use a recursive rule, you always have to know one term at least, because that term is used then to find the next one. So here it gives you u1 as well. So for example, if you know u1, you can find u2 like this. You put a 2 in here, because that means you're looking for the second term, u2. And that means if you're putting 2 in here, you put 2 in here also. And if you put a 2 in there, you get 2 minus 1, which is u1, right? So again, if 2 was substituted into this n and this n, we would get this. u2 equals 2u1 plus 5. And now you can use this rule to find the second term, because we know what u1 is. It's given to us here. So again, that u1 is replaced by negative 4. We use the rule and we can get u2. And then you can continue the same way. You can find u3. By making this a 3 and making this a 3, you can find u3. Sorry, u2, right? So you put u3. You put a 3 in there, 3 in here, and when you put a 3 in here, that works out to 2. So u3 is that. Now you're plugging u2, which you just found, into there, and you find it like that. Make sure you study this carefully. A lot of students find this a little tricky. But again, the main thing is in recursive sequences, we need the previous term to find the next one, and that's what's going on here. Okay, try these 2. And now check your answer for A. Check your work there. And now try B. And check your work for B there. So it's really important you understand how these recursive ones work. And now try these. Can you make a recursive rule for these? I'll show you the first one because, again, students find these kind of tricky. Here we notice we're always subtracting 4. A recursive rule is easier to make than a general rule because you can just write, to find a new term, you do the previous term minus 4, right? It's like saying previous term minus 4. So try B. Okay, check your work for B. In this case, it's the previous term times negative 10, so previous term times negative 10. And now try C and check there. Great, you made it. I hope those made sense. The last few were a little quick, but study it carefully, and please watch the next video now.